Okay, so at the end of my previous video, I dropped a new piece of terminology. I said we're going to talk about finite fields. So this isn't a very complex definition. A finite field is a field, I'll still call it F, and it only contains finitely many elements. The reason why we care about these is that finite fields are a valid coordinate system for performing elliptic curve calculations in, and because they only contain finitely many elements, finite fields come with a discrete logarithm problem. So again, we have a system of algebra in which a forwards calculation, such as exponents, is very simple to calculate, or maybe very quick to calculate is a better way to put that. But the reverse calculation, say performing a logarithm, is much more computationally intensive and will therefore take much longer to calculate. And this idea of a function that's easy to calculate in one direction and difficult to calculate in the opposite direction is what makes modern crypto systems secure. We can guarantee that potential attackers need to invest much more computation time than the people who are trying to keep a secret. And we can rig the deck to say, if this is the fastest algorithm that we know for solving a discrete log, then I will pick a modulus so that the logarithm will take, say, 100,000 years to calculate. And if someone can read my secrets in 100,000 years, I don't think I'll be terribly upset about it anymore. Now, every single Z mod PZ is a field, and it only has P number of elements in it. P is a prime number. So every single one of these systems that we've seen in this class is a finite field. So Z mod 2Z, Z mod 3Z, Z mod 5Z, and so on, those are all fields, including some of the more, esoteric primes that I've been throwing around. They're all finite fields. They all behave in slightly different ways, but they have enough of the familiar addition and multiplication systems that we can use them for cryptography. The point of this part of the lecture is that Z mod PZ, right, there's infinitely many examples there, but they are not all of the finite fields. There are more finite fields too. And in practical terms, most of these are good choices for performing elliptic curve cryptography. So there are some caveats. Just like we saw with the RSA encryption, you want to use a large coordinate system, or else an attacker can just brute force and quickly figure out what you're trying to protect. So exactly how many of these finite fields are there is governed by this theorem. So for every prime number p and every exponent n, which is greater than or equal to 1, there is exactly one field, and I'll call it f sub p to the n, which has p to the n as its number of elements. The number of elements in a finite field, conversely, must be the power of some prime number. So some integers do not have a finite field of that size, right? There is no finite field of order 12 because 12 is not the power of a prime number. It's 2 squared times 3 to the power 1. But for every power of any prime, there's a finite field with exactly that many elements. So there's finite fields of order 2, 3, 5, 7, 8, which is 2 cubed, 9, which is 3 squared, and so on. For technical purposes, you probably wouldn't be using smaller fields in an environment, right? So my example from the tutorial last week was a prime number with 15 digits. That's still kind of small. And also for technical reasons, you would not be using the primes 2 and 3. They interfere with some of the calculations on elliptic curves. So it's hard to imagine what these other fields look like because they don't come from the same place as Z mod out by P. But we can use some of our older tools to help better understand some of the other finite fields. So let's say that we have some finite field, and I'll call it F. And I know that it's finite, but I don't know exactly how its algebra behaves. So I know that every finite field has a multiplicative identity. That's part of what it means to be a field, and we call that element 1. I also know that every field has to be a group under the operation plus. So what I'm going to do is I'm going to say that 1 is an element of this group F, so it has to have some order, right? The order of 1 is the smallest integer so that n copies of 1 makes 0, right? Because 0 is the additive identity. So this is a tool that we've used before to understand how groups work. In the field setting, once you calculate the order of 1, that is called the characteristic of the field. And it's a fact that there's only certain numbers which are allowed to be the characteristic of a field. Those are the prime numbers. So you can have a field of characteristic 2, right? Z mod 2z is a field of characteristic 2. You can have a field of characteristic 3, or of 5, or of 7, or 11, any prime number. And we also said that if no number of copies of the element 1 gets us back to 0, then 1 must have infinite order. So fields can have infinite characteristic as well, right? So these wouldn't be finite fields. That would be more like the real numbers have characteristic infinity because no finite number of copies of the real number 1 add up to get 0. But in a finite field, we have to have a finite characteristic, and that characteristic is always going to be a prime number. And in fact, that prime number is going to be the prime in the factorization of the size of f. So to be a little bit more clear, let's look at the integer 8. 8 is a power of 2. It's 2 cubed. So there is a field which consists of that consists of 8 elements, and I'll call that f sub 8. This field has characteristic 2. So the algebra in F8 is sort of like the integers mod 2. So if X is any member of this field, it could be 1, it could be something else, then X plus X, I'd be fair to say that's 2 times X. But in characteristic 2, 2 is the same as 0. We've already seen this idea before when we were actually working in Z mod 2Z, but that continues to hold in any field of characteristic 2. So I'd say that 2x is the same as 0x, and 0 times anything is 0. It doesn't matter what x we started out with from this field. This idea that we're going to wrap around at 2 still holds in this more abstract setting, but the reason it works goes back to the fields that we've been looking at since the first week of this class. So this equation, x plus x equals 0, this would continue to work in any field of characteristic 2. So F2 is another way to say Z mod 2Z. F4 is a field consisting of 4 elements. F8 consists of 8 elements. There's an F16 because 16 is a power of 2. There's an F32 because 32 is a power of 2, and so on. I'm going to spend another mini lecture in the future to talk a little bit more about this field in particular so that we can see a multiplication table for it. But the rest of this week, I would like to explain how to encrypt entire messages on an elliptic curve, so not just the key exchange that we played around with last week. I will describe the multiplication table for F8 and show how we can do elliptic curves with stuff like that. And then that's pretty much going to be the end of the new material. So Thursday and Friday we'll have new stuff, and we will be quizzed on that the following week. But next week is our review week. So there'll be no new content there, just reviewing stuff for the final exam. All right, I will catch you later. Bye.